All right, let's talk about one of the most important but totally invisible pieces of tech that makes our digital lives work. It's the unsung hero that gets you online in seconds, and honestly, without it, the internet would be a complete and utter mess.
I mean, really think about it for a second. You walk into a coffee shop, connect your phone to their Wi-Fi, or you plug your laptop in at the office, and poof, you're online. You didn't have to fiddle with any settings, you didn't have to call for help, it just works. But how?
Well, believe it or not, it wasn't always this easy. Back in the day, it was a total nightmare. For every single device, you had to sit there and manually punch in an IP address, a subnet mask, a default gateway, a DNS server, the whole shebang. And if you got just one number wrong, no internet for you. Even worse, what if you accidentally typed in an IP address that someone else was already using? Boom, an IP conflict. And now both of you are knocked offline. Today, thankfully, it's just automatic magic. So what happened? What was the big game changer that swooped in and saved us from all that tedious, error-prone work? Well, it's time to meet the hero of our story. And that hero's name is DHCP, which stands for Dynamic Host Configuration Protocol. It actually grew out of an older protocol called BOOTP, but DHCP is what really took the idea and ran with it. It is the reason why billions, and I mean billions, of devices can get online every day without us even thinking about it. It just automatically hands out all the essential network info, making that whole manual setup a thing of the past. Okay, so how does this automatic magic actually happen? It's not really magic, of course. It's actually a super clever and incredibly fast little conversation that happens between your device and the network. We like to call it the four-step digital handshake. You can think of this whole exchange as your device basically introducing itself to the network and asking, hey, can I get the keys to drive around here? And the two main parties in this conversation are your device, which is called the DHCP client, and the network's DHCP server. At home, that's usually just your Wi-Fi router. And to make it really easy to remember, network folks have this handy little acronym for this four-step process. We call it DORA, D-O-R-A. So the D is for discover. When your device first connects, it has no clue what its IP address is supposed to be. So it sends out a broadcast message to the entire local network, basically shouting, hello, anybody out there? Are there any DHCP servers? I need an IP address. And since it doesn't have an address yet, it sends this message from the IP address 0.0.0.0. Next up, O is for offer. Any DHCP server on that network that hears that discover message will reply back with an offer. It's another broadcast that says, hey, I heard you, I'm a DHCP server, and you can totally use this IP address and these settings. It's possible on some networks that a device might even get a few different offers from different servers. The R stands for request. So your device will typically just accept the very first offer that it gets. It then sends out another broadcast message, which is the DHCP request. This one says, hey everyone, thanks for the offers. I'd like to formally request the IP address from that specific server. And broadcasting this is really important because it lets all the other servers that made an offer know, hey, thanks, but I'm good. You can take your offer back. And finally, A is for acknowledge, or what we usually call an ACK. The server that was chosen sends one last message back to the device. This is the final confirmation. It says, awesome, that IP address is officially yours for a little while. Welcome to the network. At that very moment, your device locks in those settings and you are officially online. And the craziest part? This whole DORA process happens in a fraction of a second. Now, this whole process seems pretty straightforward, but it's not a total free-for-all. To stop things from turning into chaos and to make sure addresses are used efficiently, DHCP has a very strict set of rules, and it all starts with the address pool itself. And probably the most important rule to get your head around is this. Your IP address isn't a permanent gift. It's a rental. The DHCP server doesn't just give you an address to keep forever, it only leases it to you for a specific period of time. This lease is so important. Imagine a busy airport where IP addresses were permanent. Every phone that ever connected would take an address and never give it back. Pretty soon, they just run out. By leasing, addresses get recycled automatically. So when your lease is halfway done, at the 50% mark, your device quietly asks the server to renew it. If that doesn't work for some reason, at the 87.5% mark, it gets a little more desperate and starts shouting for any server to give it a new lease. If it still gets nothing by the time the lease is 100% expired, that IP address goes right back into the pool for the next person. So where do all these rentable addresses come from? They come from something called a scope. A network admin sets up this range, creating this pool of available IP addresses that the DHCP server is allowed to hand out. This also makes sure the server doesn't accidentally give out an address that's already being used by something important, like a server. But what if you have a device that needs to have the same IP address every single time? Like a network printer or a file server. For that, we use what's called a reservation. An administrator can just tell the DHCP server, hey, whenever you see this specific device's unique hardware address, its MAC address, I want you to always give it this exact IP. It's kind of like having a reserved parking spot in the network's giant parking lot. So far, this all works beautifully inside a single, simple network. But what happens in a big company where you might have dozens of different networks or subnets all separated by routers? Well, this is where we run into a major DHCP challenge. Here's the core of the problem. Remember that first discover message, the big shout out into the network? Well, that's a broadcast. And routers, by their very design, are built to stop broadcast traffic. They act like gatekeepers to keep all the local network chatter from flooding out everywhere else. This means that a DHCP discover message is basically trapped in its own little network segment. So, how can a device get an IP address if the main DHCP server is on a completely different network? The solution is actually pretty elegant. It's something called a DHCP relay, which you'll also hear called an IP helper. It's a special feature you can turn on in a router that basically tells it to act as a helpful middleman. This lets a big company have just one central DHCP server that can manage IP addresses for tons of different networks all at once. Here's how it works. When a client sends out its broadcast, the router that's set up as a relay grabs it. But instead of just dropping it, the router repackages that request into a targeted direct message, what we call a unicast, and sends it straight to the remote DHCP server's address. The server then sends its offer directly back to the router, and the router passes it along to the original client. It effectively builds a bridge for that DHCP traffic, allowing it to cross between networks. So, when you put it all together, from that simple 4-step handshake to these clever relay agents that can span entire corporate networks, you really start to see how DHCP has become this absolutely essential, critical part of our modern world. And the scale is just mind-boggling. Every single day, billions of devices, phones, laptops, smart TVs, all those little smart home gadgets, they all rely on this invisible automatic process to connect to the network. Without DHCP, the internet as we know it would just grind to a halt under the crushing weight of manual configuration. It just wouldn't work. DHCP is the perfect example of a foundational technology that works so well, we completely forget it's even there. Which kind of makes you wonder, doesn't it? What other invisible protocols are humming along in the background right now, quietly powering your entire digital world? Thanks for joining me.